Hi everyone, in this video I'll be covering projectile motion. I'm going to begin with a brief overview of projectile motion, and then we'll dive right into 3 example problems that I was able to come up with. So, projectile motion concerns the trajectories of launched objects, and like free fall, objects accelerate down at g equals 9.8 meters per second squared on Earth, so you should always remember 9.8 meters per second squared on Earth, but on the moon, for example, we see g equals 1.6 meters per second squared, and I have one problem in these examples that takes place on the moon. And to solve a typical projectile motion problem, we use trigonometry to split motion into horizontal and vertical components. The horizontal component of the velocity is constant, while the vertical component experiences constant acceleration. So there's no component of the acceleration in the horizontal direction, and that means the acceleration is 0, and the horizontal component of velocity must be constant. We can use any kinematic equations on the vertical component. Alright, so projectile motion concerns objects launched with some horizontal component to their initial velocity. Here's a nice little sketch of a typical projectile motion problem. We have a cannon, and it launches a cannonball, and it splats on the ground some distance later. I have v0, the initial velocity, drawn here, but maybe you're given v0, maybe not. Doesn't really matter. But compare this with free fall problems in which an object is launched straight upward or downward. Projectile motion is more general and therefore more difficult. So in projectile motion we have some horizontal component to the velocity, and so this is a manifestly two-dimensional problem. We have to work it out in 2 dimensions. Let's talk about taking these components. Because the acceleration vector points directly downward, only the vertical component of the velocity changes in projectile motion. Again, take the horizontal component of that acceleration vector and you get 0. So 0 acceleration in the horizontal direction, and that means the velocity, the horizontal component of the velocity must be constant. The horizontal component is constant. That means that we can always use x equals vx times t plus x naught. Displacement equals velocity, or x component of the velocity in this case, times time plus initial displacement. This is an old standby from 8th grade. You should remember it coming into this class, and please remember it going forward from this point. You really should have, you've seen it several times now with the sequential kinematic equations problems that we've done. It's an old equation that you should be very familiar with. So, yeah, don't forget the old good equations. So where Vx is constant, like I said. Now, because it's constant, I do tend to write it in a couple of different ways. I may occasionally write it as Vx naught. That's the initial x component of the velocity. If I write this in a different color elsewhere, I'll just say that I sometimes write it as V naught x. But because the horizontal component of the velocity is constant, there's only ever going to be one horizontal component of the velocity in the entire problem. And so Vx, V naught x, and Vx naught are all going to represent the same quantity. They're all going to be the same. Just want you to know that my notation can be a little bit ambiguous in that way. Okay, for the vertical component, acceleration is constant, and we can use any kinematic equations we want. We tend to not use y equals, average displacement is, net displacement, y minus y naught. Net displacement equals average velocity times time. Okay, so the second kinematic equation. We tend to not use it because we're typically given g equals 9.8 meters per second squared. Whenever you have a problem that takes place on Earth, you know that g equals 9.8 meters per second squared. And this kinematic equation does not involve acceleration. If we're given acceleration, we might as well use a kinematic equation that involves acceleration. And so there's rarely much reason to use this. I could come up with some sort of a problem where it takes place on an unknown planet where you don't know the gravitational acceleration. But barring something like that, you'll pretty much always want to avoid this kinematic equation and instead use the other 3 kinematic equations, which all involve acceleration. Okay, so let's talk briefly about air resistance because students always like to ask about air resistance. In an introductory course, it is always necessary to take air resistance to be negligible. And to be perfectly clear about that, I'll say that in a quantitative problem where you're putting numbers to it, yeah, you will always take air resistance to be negligible. That should be written out explicitly in the problem statement or otherwise made clear. Maybe it takes place where there's no atmosphere, and so if there's no air resistance. I could ask potentially a qualitative question that involves air resistance and say, if I were to kick a soccer ball straight up into the air, how would its motion compare with air resistance versus without? Which one takes longer to hit the ground, something like that. So this is often reasonable when the object is very dense, such as a cannonball. Cannonball is made of iron, it's a small, round, compact object, and so the air is not going to dramatically influence it, the way that it would influence a feather's motion. So if air resistance were not negligible, acceleration would not be constant, and we could not use the kinematic equations for the vertical component of motion, and the horizontal component of velocity would not be constant. So basically we'd be completely screwed. We would not have any way of doing these problems because everything that we've done so far has depended on constant acceleration, and you get non-constant acceleration in both components, and it just becomes unsolvable. So air resistance tends to slow things down as long as there is no wind. Basically, the objects tend to get carried along with the wind or air, and so if the air isn't moving, then the objects will tend to stop relative to the air. They'll tend to stop relative to the air, which, if it's not moving relative to the ground. Okay, so it slows things down. With all of that said, let's jump straight into some examples. So a cannon is fired from a high tower, 56.5 meters above the ground, and the initial velocity of the cannonball is 44.7 meters per second at 26.6 degrees above horizontal. Determine A, how long the cannonball remains in the air, and B, how far it travels horizontally. Neglect air resistance. So again, you're always going to be told to neglect air resistance, but you should look for that phrase in the problem statement anyways. Well, here's an example, or here's a sketch of this situation. Now, I have a lot of information here. I would recommend pausing the video because you'll need some time to digest it all. But the point is that you're given y naught, you're given v naught, and you're given theta, this angle. And basically you want to find out how long it stays in the air and this range x, okay? But the way that we'll do that is we'll break up the velocity into x and y components. So here's the x component, here's the y component. Previously we'd studied these riverboat problems or two-dimensional addition of relative velocities. These problems are a little bit different, but the common theme that I would like you to see is that whenever you have angles involved, or whenever you have angles involved or otherwise two-dimensional problems, your immediate goal is going to be to break everything up into horizontal and vertical components. So break everything into horizontal and vertical components. Okay, so with that said, let's jump right in. Part A asked for the time that it stays in the air. The first thing that we'll need is the y component of its velocity, because we don't really care where it is horizontally. This thing could be launched, it could dribble out of this cannon here, and that would give us some similar information about the time that it spends in the air. So the time that it spends in the air is governed by the y component. And so let's find the y component of its initial velocity. So v naught y is equal to v naught times the sine of theta. I'd like you to see that. So here's the initial velocity. It's the hypotenuse of this right triangle. Here's the vertical component. Here's theta. The vertical component is opposite the angle theta, and we have the hypotenuse, and so we'll use SO, or sine, from our SOHCAHTOA mnemonic. All right. So that was, what were those numbers? 44.7 meters per second times the sine of, what was this value? 26.6 degrees. And when I plug that in, what I find is that the initial y component of its velocity is 20.0 meters per second. Okay, this is not a result. This is not the answer that we're looking for, but it's our first step in that answer, because we initially had the velocity in terms of its magnitude and direction, and now we have at least one component of the velocity. So let's carry on from there. We need to know the time that it spends in the air. We'll need a kinematic equation that involves initial velocity, which we just found, acceleration, which is 9.8 meters per second squared downward. Let me, by the way, I always should do this first. I do tend to slip up. Let's draw a coordinate system, and in fact, I'll even be good and specify where it is in relation to everything else. So let's put the coordinates at the bottom of this tower. That seems reasonable. Okay. So we need a kinematic equation that involves the initial velocity, which we just found, the acceleration, which is 9.8 meters per second squared downward, and time, as well as because we're solving for time, as well as the initial displacement. Well, think about those variables, and what you should come up with is the third kinematic equation. So y is equal to, I'll go ahead and already write negative 1/2 gt squared. So negative because the acceleration is in the downward direction. I'll briefly sketch it out, but I'm not going to do it for every problem. We would take the y component of this acceleration, and because the acceleration is downward, it had better pick up this negative sign. And the acceleration is g. Okay, so negative 1/2 gt squared plus v naught y times t plus y naught. Well, where does the cannonball end up? According to our coordinate system, it ends up at y equals 0. Y naught is given to us, and pretty much everything is given to us except for t. So since this is a quadratic equation, I'm going to go ahead and plug in numbers right now. Now, negative 1/2 g is negative 4.9 meters per second squared. 4.9 meters per second squared times t squared plus v naught y, which we found was 20.0 times t plus y naught, which I said in the problem statement was 56.5 meters. Let's leave the units off for the intermediate steps. So there's 56.5 meters as our y naught. Solve this quadratic equation. In the interest of time, I think I'm gonna skip that step. But just know your quadratic formula. Be prepared to plug in those numbers. But what you'll find is that t equals, I will write this out, negative 20 plus or minus, maybe I'll make it positive 20. We'll do positive 20 because both the numerator and the denominator are negative. So positive 20 plus or minus the square root of 20 squared plus 4 times 4.9 times 56.5. So I said I would skip doing the quadratic formula, but I'm basically doing it right now. And the only reason I'm doing it, I'm perfectly content with you just using your calculator and getting the result as quickly as possible. But the real reason I'm doing it is because there's this plus or minus sign here. In fact, what goes under the square root sign is 20 squared, so something, and plus a little bit, so it's something a bit larger than 20 squared. And so when we take the square root of this, it's going to be something larger than 20. I'm not quite sure what it'll be. I don't really care to calculate it, but the point is that it'll be something larger than 20. Here's the deal. You'll get two answers. One of them will be positive and one of them will be negative. And time for this problem, we'll want to be positive. We want to take the positive value of time. There is some physical significance to the negative time. If we were to trace this cannonball's trajectory backwards and pretend that the cannon isn't there at all to stop its motion, it would continue back through time and space and then end up somewhere down here on the, inside this cliff that the cannon is mounted on. That's clearly non-physical. We want to omit that, and so we'll keep the positive value and omit the negative value, and we get 6.00 seconds. This is a result. This is the special time at which the cannon hits the ground at y = 0, because it satisfies this kinematic equation for the values that we plugged in. So there we go, there's part A. Part B asked how far it will travel. And then the first step for that is going to be finding the x component of its velocity. Now I could write it as vx, but I'm going to write it as v naught x. V naught x is equal to v naught times cosine of theta. Let's convince ourselves of that. Here's the horizontal component. Oops. Well, there it goes. Okay, here's the horizontal component. There's the hypotenuse of the vector. That's v naught. And there's theta. V naught x is adjacent to our angle, and so we'll use cosine. And so it's v naught times cosine of theta. That's according to SOHCAHTOA. This is, do it on a separate line. This is 44.7 meters per second times the cosine of 26.6 degrees. All right. And what I get when I do that is 40.0 meters per second. Again, this is not a result, but it's a nice intermediate step. If we want to know how far this cannonball goes, we need to know how fast it's moving in the horizontal direction. Well, it stayed in the air for 6 seconds, and the horizontal component of its motion, of its velocity, is 40 meters per second. So how far does it travel? X is equal to v naught x times t plus x naught. We can say that it starts at x = 0. And based on how I chose my coordinate system, yeah, it starts at x = 0. And let's plug in numbers. So that's 40.0 times 6.00, 40.0 meters per second, 6.00 seconds, and what I get is 240 meters. And if you like significant figures, this 0 is significant. If you like scientific notation and you don't like putting bars over significant digits, then you can do 2.40 times 10 squared meters. Either of those is perfectly acceptable. But that's how far it ends up away from where you launched it. So, pretty straightforward problem. We found out that the cannonball stays in the air for 6 seconds, and it has a range of 240 meters. I think that was all quite doable. It's just a matter of picking the appropriate kinematic equations to use and breaking these velocities into components. That was a crucial step. Onward to example 2. Alright, example 2. You are on the moon where g = 1.6 meters per second squared. I don't want you thinking that there's anything special about 9.8 meters per second squared. It's just special to Earth. So here's a problem that takes place on the moon where g is 1.6 meters per second squared. And you're playing catch with a friend. You throw a ball at 25 degrees above horizontal, and your friend, who stands 15 meters away horizontally, catches it after 2 seconds. So we're given what looks like very little information, but we'll be able to answer all of these questions. So, part A, what was the horizontal component of the ball's velocity? Part B, what was the vertical component of the ball's velocity? Part C, what was the ball's initial speed? Part D, how far above or below you is your friend? And part E, how fast was the ball traveling when your friend caught it? Now that you've seen one example, go ahead and pause the video. Please always pause the video whenever we go over examples and try and do them yourself. But the basic strategy is going to be to break the velocity into components and apply some kinematic equations to the vertical component, and x equals v times t to the horizontal component. Okay, so part A was what was the horizontal component of the ball's velocity. Here's a little sketch of this situation. Here you are on the moon, and you throw the ball at some speed v0, and you throw it at 25 degrees above horizontal. Your friend stands somewhere above you, and they're 15 meters horizontally away. They're not 15 meters along this hypotenuse away, but just horizontally, just the horizontal component of their displacement. Okay, part A. We wanted the horizontal component of the ball's velocity. Well, they stand 15 meters away, and they catch it after 2 seconds, and so x is equal to v0 x times t plus x naught. Again, I'll be good. Draw some coordinates. And this is already a very busy figure, but I'll overlay this where I'm setting the coordinates. In fact, it'll be right where the ball starts, just to be explicit about it. Okay, so x is equal to v0 x times t plus x naught. Never mind that I have 15 meters marking from foot to foot, and yeah, same with y as that goes from your foot to their foot. But x naught, the point is that it's where x naught is where the ball begins its motion, so x naught is 0. Okay, x is 15 meters, and t was 2 seconds. You were told that your friend catches it 2 seconds later. So this tells you that v0 x is equal to x divided by t, which is 15 divided by 2, which is 7.5. That's the appropriate number of significant figures, but I'll just tack one more on because I feel like it. Okay, 7.50 seconds. If I were writing this problem more carefully, I would write 15.0 meters and 2.00 seconds. All right, and that's it. That's the x component of the initial velocity. Part B asked for the angle at which you launched the ball. Okay. Did it? No, I'm sorry. We have the angle. Part B asked for the vertical component of the ball's velocity. So now what we have are the x component of the velocity and the angle. And so we want the y component. That's what we're trying to find. Okay. So what we'll use is some SOHCAHTOA, and we want the part that involves the opposite side, which we're interested in, v naught y, and the adjacent side, which we have. And so that's tangent, TOA. So tangent of theta is equal to v naught y, the opposite side, divided by v naught x, the adjacent side. This tells us that v naught y is equal to v naught x times the tangent of theta, which is 7.5 times the tangent of, what was the launch angle? 25 degrees. 7.5 times the tangent of 25 degrees. All right, plug in those numbers, and what you should find is that the y component of the initial velocity is 3.50 meters per second. Again, I'm technically keeping one more significant figure than I should, but yeah, 3.5 meters per second. Okay, part C. Part C asks for the ball's initial velocity, Now, it turns out that we don't actually need that to do any other parts of the problem. So part C is a little bit of a digression. But the point is that we have the x component and we have the y component. So what I will suggest we do is use the Pythagorean theorem. And we'll use v naught is equal to, or let's do it explicitly. V naught squared is equal to v naught x squared plus v naught y squared. And v naught x was x divided by t squared. V naught y was v naught x times the tangent of theta, so that's x divided by t squared times the tangent squared of theta. I like doing things algebraically. So v naught is equal to x divided by t times the square root of 1 plus tan squared theta. Okay. You could just as well go back up here, square root both sides, and just plug in numbers, because we found 7.5, no, sorry. Oh, my mistake. I wrote 7.5 seconds. This should be 7.5 meters per second. Okay. You could just as well take v naught x, square it, add v naught y squared, and then square root it, and proceed numerically. Now the point is that what you'll find is v naught is equal to 8.28 meters per second. There you go. Part D. Part D asked how far above you your friend is. So what we have is the initial y value, which is 0. We have the y component of the velocity, that's important. We have time, and we have g. And so we'll want a kinematic equation that involves y, g, t, and v naught y. Think about it for a minute. I hope you thought of the same thing that I did. Y is equal to -1/2 gt squared plus v naught y times t plus y naught. Where does the ball start? It starts in your hand, which is the origin of our coordinate system. So that's 0. And then everything on the right-hand side is actually given to us. So I don't need to do any algebra. I don't need to do any quadratic formula or anything like that. I'm just going to get -1/2. Be careful, because this is no longer 9.8. This is 1.6 meters per second squared. Times, instead of t squared, we'll do 2 squared, because it takes them 2 seconds to catch it. Plus v naught y, which was 3.5 meters per second, times 2, and then plus 0 if you want, because y naught is 0. Add all of that up, punch that in on your calculator, and what you should find is that it's 5.39 meters. So your friend is 5.39 meters above you. It's actually quite a ways, but whatever. All right, so they're 5 meters above you. They're up a tall hill. Also, that value is positive, and so that tells you that they are above you. If you tweak with the numbers a little bit, then you could actually make your friend stand on the same level as you or below you, in which case you would get a negative value. Okay. Part E. Part E asks for the speed of the ball when your friend catches it. We have the initial y component of the velocity. So let's find the final y component of the velocity. We'll call that Vy. This is the, not V naught y, but the final y component of the velocity at some later time. And what we have are the gravitational acceleration g and the initial y component and time. And so which equation are we going to use? Which kinematic equation will we use? we'll use this one. Negative g t plus v naught y. And we can do a little bit of algebra. V naught y I had was x over t times tangent of theta, if you want to write it only in terms of given quantities. But the point is that if you plug in those values, negative 1.6 times 2 plus 15 over 2 times the tangent of 25 degrees, I think those are the values, what you should find is it's 0.297 meters per second. Okay, again, not a result. That's only the y component of the final velocity. The total final velocity, v, no subscripts on this one, it's just the final velocity, so it's not v naught, it's not vy, not vx. Let's use the Pythagorean theorem here. V squared is equal to vx squared plus vy squared. Vx squared is a constant, it's the same as v naught x. But I'm dropping the naught subscript to emphasize that this is the x component of the velocity when your friend catches it. And vy is the final velocity, which we just calculated. It's 0.297 meters per second. So, by the way, the ball is still traveling upward at that point. It hasn't yet peaked at that point because the velocity isn't zero at that time. Again, you can just plug in values. I'll try and work algebraically. So, Vx was constant. It was x over t squared. And then Vy, yeah, I don't want to bother squaring all of this. So we'll work numerically. It's time to plug in numbers. We can do it. You can work algebraically. But let's just work numerically. Vx we had was 7.5 meters per second, but we square it. And Vy was, we just found it, 0.297 meters per second, but we square that value as well. Square root them because we're using the Pythagorean theorem. We have the x and y components, and so to find the total final velocity, you square them, add them together, and then square root them. What do we get? Well, I get 7.51 meters per second. So that's very close to the just the x component of the velocity, which was 7.50 meters per second. And it tells you that the most of its velocity is in the x component. There's very little in the y component, and that agrees with what we see up here. So that's another problem. That's another projectile motion problem. And I've got one more for you guys. Third example. Odysseus wishes to shoot an arrow through two axes that stand in a window 20 meters above the ground he stands on. For the shot to be successful, the arrow must be traveling perfectly horizontally as it passes through the axes. Odysseus can fire an arrow at 30 meters per second. At what angle relative to horizontal should he aim? Part B, how long does the arrow take to reach the axes? And part C, how far should he stand from the window? And we'll take air resistance to be negligible. Always look for that phrase. Air resistance is negligible. Alright, here's a little sketch. Here's Odysseus drawing back the bow. And I'll remember this time to draw our coordinate system. Here's X and Y. What I'll do is I'll put it directly on top of the place where the arrow is released from, but I don't want to do that just yet because I want to make sure you get a good chance to look at this figure. So he shoots it at 30 meters per second with this vertical component at some unknown angle theta. It has components v naught x and v naught y. And we want the arrow to level off such that it flies directly horizontally through these two axes that are sitting in this window, and the axes are 20 meters above where he stands. Okay. All right, so this is basically illegible, but whatever. Part A. Part A asked, at what angle should he fire it? What we'll first need is the y component of the velocity of this arrow. So let's use a kinematic equation that involves y, because we know how high up it must go, 20 meters. V naught y, which we would like to solve for, and g, which is 9.8 meters per second squared. So we're given g. Think about it. Think about it for a little while. But what you should come up with is the kinematic equation that doesn't involve time. And so vy squared minus v naught y squared is equal to negative 2g y minus y naught. Okay, so that kinematic equation doesn't involve time. It involves a bunch of quantities that we know. What is the final velocity of this arrow as it flies? Y component of the velocity of the arrow as it flies through the axis? Well, it's reached the top of its path. We're told that it has to be flying directly horizontally, and that means that it's traveling neither up nor down. So the peak of an object's path, or the place where it's traveling horizontally, corresponds to a place where the y component of velocity is 0. Likewise, for y naught, that's the place where Odysseus stands, and so this is also going to be 0. And so what we'll get is, well, I'll get rid of the negative signs, and we'll get v naught y squared is equal to 2g y. And therefore v naught y is equal to the square root of 2g y. All right. Plug in some values. That's the square root of 2 times 9.8 times 20. And what I get is 19.8 meters per second. Now, again, I'd like to emphasize that this is not a final result. You were asked what angle does he fire this bow at. All we did was find the y component of the velocity. But we have the hypotenuse. We have the initial velocity of the arrow is, or initial speed of the arrow is 30 meters per second, and we have the y component. So let's use some trigonometry. We have the side opposite theta, and we have the hypotenuse, and so that's begging for sine, for so in SOHCAHTOA. And sine of theta is equal to v naught y divided by v naught. We just found v naught y, and we were given v naught. And that means theta is equal to the arc sine, or inverse sine, v naught y divided by v naught, which is the inverse sine of 19.8 divided by 30. And again, if I want to keep more significant figures, I should write 30.0. But the point is that what you'll get is 41.3 degrees. Okay, so that's part A. So we know that he has to fire it at 41.3 degrees. We don't know where he's standing, but we know that wherever it is, he's firing it at 41.3 degrees. Part B asked, when does it reach the axis? Okay, so we don't need the horizontal component of the motion to determine when it reaches the axis, because the time when it reaches the axis is when the arrow is flying horizontally. So again, we'll work with the vertical component of the motion, and that means working with kinematic equations. And so that's Vy, the final velocity, final y component of the velocity, is equal to negative gt plus v naught y. Vy is still 0. It's flying horizontally when it travels through the arrows, and so there's no vertical component to its velocity. And that means t is equal to v naught y divided by g. Well, we found v naught y in an intermediate step of the previous problem. It was square root of 2gy, and so I could write this as the square root of 2gy over g, or the square root of 2y divided by g, which is the square root of 2 times 20 divided by 9.8. And I get 2.02 seconds. And that is what we were asked for. Finally, part C. Now we want to know how far away Odysseus must stand for the arrow to go through the axes. Let's find the x component of the velocity. There's a couple of different ways to do that. We can use the angle that we found and use some trigonometry. So we would take the hypotenuse of 30 meters per second and multiply by the cosine of the angle. Or what I'll do is I'll use the Pythagorean theorem. So I'm going to take this 30 meters per second, square it, subtract v naught y squared, which we have, and that will give me, if I square root it, that'll give me v naught x squared. So again, v naught x squared plus v naught y squared is equal to v naught squared. This is just the Pythagorean theorem. The x component squared plus the y component squared is the hypotenuse squared. And that tells us v naught x is equal to the square root of v naught squared minus v naught y squared. The video is getting a little bit long, and I'm getting a little tired of doing algebra, so I'll plug in numbers immediately. V naught was 30, and v naught y was 19.8. Carry out this calculation, and what you should find is 22.5 meters per second. That's the horizontal component of the initial velocity. It's not what we were asked for. We were asked for the distance that he has to stand from the axis, horizontal distance that he must stand. So we then turn to x is equal to v naught x times t plus x naught. He's standing at x equals 0. We'll solve for x. We just found v naught x, and so that's 22.5 times 2.02 was our time, t. And what I find is that that's equal to 45.5 meters. Okay. And that does it for part C of this problem. So there were a lot of equations that went by, a lot of different steps. Basically, your strategy for solving these kinds of problems is to just throw as many equations as you need to at the problem until you end up with the result that you're looking for. With practice, you get a little bit better at figuring out which equation you want to use and when. And oftentimes the problem statements have hints by way of the order that they ask you to solve for things. So when I wrote these 3 problem statements, I made sure that that you could always do part A before you do part B, and so on. Okay, but I'd like to talk about writing your own problems. I think that that's a skill that every student should know with regards to most of the physics problems that you do. And I've talked a little bit about this in the past, and it varies from subject to subject. But for projectile motion problems in particular, writing a projectile motion problem is fairly simple. Based on the equations involved, you need to provide exactly 4 pieces of information to obtain a solvable problem. And sometimes problems will have 2 solutions. Actually, they'll sometimes even have 0 solutions if you pick some bad numbers. But pick 4 quantities to be provided from the following list, and usually you'll be able to solve for all of the other variables. So here's this list I came up with. G, that's your gravitational acceleration. Often it's given as g equals 9.8 meters per second squared. If the problem takes place on Earth, then g will be given to you, and then you just need to come up with 3 variables, 3 quantities to be given. So that's not bad at all. Y minus y naught, the net vertical displacement. I could have written y and y naught separately, but typically one of these is going to be 0. So I'm just going to say that specify one of them, specify that the other one is 0, and you've pretty much done your job. X minus x naught, your net horizontal displacement. Same story there. T, your time of flight. Sometimes, I avoided this in this video, but sometimes we use capital T. You basically plug it in your kinematic equations and things exactly as you would lowercase t. But capital T sometimes is used to emphasize that it's the time of flight. It's from when the projectile was launched to when it struck whatever it was launched at. V naught, the initial speed of the projectile. V naught x, the horizontal component of the velocity, initial horizontal component of the velocity. V naught y, the initial vertical component of the velocity. Vy, the final vertical component of the velocity. And Vx, of course, is going to be the same as the initial horizontal component of the velocity. V final, the final speed of the projectile. On the last problem, I just use V, or maybe in a couple of places I just use V without any subscript. But the point is that it's the final speed of the projectile. Theta is typically the launch angle. In all the problems that we worked with here, it was with respect to horizontal. One way to trick your friends is to make it with respect to vertical, and then your sines all become cosines and your cosines become sines. So I don't ever want you to think that sine is associated with vertical and cosine is horizontal as it is in your math classes. And theta final I'll describe as the angle of impact, so you basically use the same trigonometric decomposition on the initial velocity as you do in your final velocity. So if it takes place on Earth, you just need to pick 3 variables from this list, and the 4th variable will automatically be given to you. If you don't have it take place on Earth, you should probably have it take place on planet X or some strange place where you don't know what the gravitational acceleration is, and then g would be a variable, and you need to give 4 other pieces of information. Let's look back through these examples really quickly, and I'll try and convince you that that you're given all these pieces of information. For the first problem, we had this take place on Earth, where g is 9.8 meters per second squared. We gave y naught, we gave v naught, and we gave theta. There's 4 pieces of information. Second problem, we had g, 1.6 meters per second squared on the moon, theta, x, and t, the time of flight. 4 pieces of information. And for this last one, again, it took place on Earth. G equals 9.8 meters per second squared. We were given y, the final height of the projectile. This one was tricky. It needed to be traveling perfectly horizontally, and so we were given vy, which is 0 in this case, and v naught. So those are the 4 pieces of information. I've underlined 4 things in green. So hopefully you can believe that if you write up some sort of a story, as I did, and then basically pick 4 things to be known quantities, then you can write your own projectile motion problems and then practice them and get better at them. Share them with your friends. So I hope that this has been instructive to you, and I will see you next time when we talk about circular motion. So bye-bye.